When taking derivatives, you start with a function, take its derivative, and end up with a new function called the derivative function. Well, what if we reverse this process now? What if we start with a function and then ask the question, what function would I need so that when I take the derivative of that function, I end up with the function I started with? So it's basically thinking in reverse. So we call a function capital F an antiderivative, and notice here it's an and not the antiderivative. It's an antiderivative of lowercase f, provided that when we take the derivative of this capital F, we get the derivative function which is equal to the function lowercase f. That is called an antiderivative. So let's take a look at an example. So we want to find an antiderivative of the function f of x equals x. So we're asking the question, what function do I need that when I take its derivative, I end up back with the function f of x equals x? Well, let's try this function here. Capital F is equal to 1/2 x squared. When you take its derivative, indeed you get back x, and hence capital F of x is an antiderivative of lowercase f. But there wasn't just one function that worked. I mean, take a look at capital G of x. This is 1/2 x squared plus 7. Let's take the derivative of capital G. When we do so, we also end up with x. And so g of x is also an antiderivative of f. And so how did this happen? Well, take a look at this plus 7 here. It's a constant. The derivative of any constant is 0. So we could have started out with capital F and added any constant that we want and end up with a function that is an antiderivative of lowercase f. And that's how antiderivatives work in general. So let f be any antiderivative of our lowercase f function. Then all antiderivatives have the form f plus c, so where c is an arbitrary constant. What that's telling you is that once you have one antiderivative, then it'll at most differ by another antiderivative with the addition or subtraction of a constant. So we need a way to discuss the entire family of antiderivatives rather than one particular one. And this concept is the indefinite integral. And what is the indefinite integral? Well, basically you find one antiderivative and just write a plus c. But that c is extremely important, as we've just seen that this c represents all possible antiderivatives. Now, why we use this symbol and why we're calling it an integral, to be precise, an indefinite integral, will become clear when we discuss the fundamental theorem of calculus. For now, we're just going to think about the indefinite integral as an antiderivative plus some arbitrary c, which we write just a plus c at the end of one antiderivative that we found. So some things that might help when computing indefinite integrals are these two rules. So we have the constant multiple rule, that if you have a constant multiplied by a function, you can pull it out of the indefinite integral. And so this works for any real number c. That's the constant multiple rule. And we also have the sum rule, so that if you're trying to find the indefinite integral of two functions added or subtracted, well, you could break up the problem and find the indefinite integral of one and add it to the indefinite integral of the other function. if, of course, there was a plus sign between those two. If there was a minus sign, you would subtract in that case. So what you see here are common indefinite integrals. This here is basically the power rule. So when p is not equal to -1, then to integrate this expression, here we call this the integrand, that's between these two symbols called the integrand. So when you have an integrand x to the power p, say for example x squared, then the indefinite integral of that is equal to x p plus 1. So if we used x squared, then we would have x to the power 2 plus 1, so x cubed, all over p plus 1, which would be 3 if p was equal to 2. Plus this arbitrary yet very important c that one should not forget. What about if p was equal to -1? Well, then here we get that the indefinite integral is equal to natural log of the absolute value of x plus c. And we could also see some trigonometric functions here. In all of these, if you don't believe that, say sine x plus c is the indefinite integral of cosine x, well, take the derivative of this. Okay, what's the derivative of sine x plus c? It's cosine x. So indeed, this works. So let's take a look at an example. We want to compute the indefinite integral of 2x plus 3 cosine x. Well, we're going to take advantage of these rules that I discussed above, the sum and constant multiple rule. So first I'll take advantage of the sum rule. This could be considered some f and this g. So then you could, quote, break up or distribute the indefinite integral through to each of these expressions. And then I'm going to take advantage of yet another rule and factor out that 2. Okay, and that's taking advantage of the constant multiple rule. And factor out a 3. That's in front of the cosine x. 2 and 3 are real numbers, so this should work. And now I'll compute the antiderivative of x. Well, take a look at the power rule here. That would be with p equals 1. And so I should get x to the power of 1 plus 1 all over 1 plus 1 plus c. And so there's the indefinite integral of x in parentheses there. And likewise for cosine x, we could just take a look and see that that's the indefinite integral. And so we get that sine x plus some constant that I call c sub 2. Okay? Well, what's really important is just that you have a c at the end, right? It doesn't matter that this big capital C that I leave at the end after I simplify this expression is actually equal to 2 times c1 plus 3 times c2. It doesn't matter. That constant at the end is just to express the fact that you have a family of antiderivatives. So all we really care is that it's just some c, and we don't care precisely how that c was built. So we're just going to absorb all the other constants into that one capital C, and we will then have the indefinite integral of what we started with. In this next example, we'll get to see the importance of this constant c that we attach to the indefinite integral. So here we're asked to find the position function, x of t, for a particle that has a velocity function, t plus sine t, and initial position, x of 0 equals 1. So here, when the clock starts at t equals 0, this particle is along the x-axis at 1, for example, 1 meter. So first thing, notice that the velocity is the derivative of the position function. So what does that mean? That means the position function is an antiderivative of the velocity function. Wait a second. If the position function is an antiderivative of the velocity function, why are we then asking for the position function instead of a position function? Well, we're also told the initial position, and that's going to help us to solve for C and get a unique antiderivative that fulfills this condition. So let's take a look at how that happens. So okay, x of t is the antiderivative of v of t, so let's then integrate v of t. So we do the indefinite integral of v of t, and we end up with 1/2 t squared minus cosine t plus this capital C, which luckily we did not forget. So, okay, we have the family of antiderivatives there. Now we want not just any good old-fashioned antiderivative, but one that satisfies that condition. And to satisfy that condition, here it is. This part here is given. We're told that the initial position is 1. But what you see on the right over here is what we get when we plug t equals 0 into our indefinite integral result. Okay, so if you plug in 0 into all of these, you'll have 1/2 0 squared minus cosine of 0. We just plugged in 0 wherever we saw t. And so the right-hand side here will reduce down to minus 1 plus c. Okay, and what that allows us to do is then solve for this unique c that would not only give us the antiderivative of the velocity, but also ensure that the initial position was 1. And that c would be equal to 2. And so here is our unique position function, the unique antiderivative that also satisfies x of 0 equals to 1. And you can check that. So we can check these two conditions. First, we could take the derivative of the right-hand side and notice that we are indeed returning back to the velocity function. So we have an antiderivative. But on top of that, when we plug in a 0 into this function, we'll get 0 minus 1 plus 2, which would equal 1, and hence we also satisfy that second condition. So if you were frustrated that you might have lost some points on an exam because of that, quote, stupid C, well, it's extremely important, actually, to remember that, because without that C, we can't solve problems such as those that you have seen in this second example.